Number 2 homework on limits. On the first problem, we're going to use the given graph to find the limit. It says the limit as x approaches -1 from the right. That plus means from the right. So you are coming in from the right-hand side to -1. And you can see at 2, we're up here at 4. And at 1, we're up here at 4. And at 0, we're up here at 4. And so as I get closer and closer and closer, I know that arrow looks terrible. So I get closer and closer and closer to -1, I am approaching 4. Now I know that when I actually hit -1, I'm undefined at 4 because of the open circle, but that's not what a limit is. The limit is asking what I'm approaching, and I am approaching from the right-hand side 4. You can see from the left-hand side I'm approaching -4, and you can see that if I asked you what the limit was without the plus sign, that limit would not exist because I'm approaching 2 different places from the left and the right-hand side. All right, let's look at number 2. The limit as x approaches -1 from the left. See the minus sign? So I'm out here and I'm coming in to -1. And you can see that as I'm approaching, you can see where the function is. As I'm approaching -1, that value here from the left-hand side is going to be at -7. So this equals -7. Now, if you had wanted to actually use the piecewise function instead of the graph, the piece that you would use would be the piece that's on the left-hand side, which is that first piece. And so I just want to show you quickly how if I were to plug in -1 direct substitution into that first part of the function, I would have negative and then -1 subtract 8. And this is equal to 1 subtract 8, which is also equal to -7. So this second method I solved using direct substitution. On 3 and 4, I'm simply going to use the graphs because they are given to find the limit. The limit as x approaches -3. There's no little plus or minus, so I'm approaching from the left and the right side to -3. So from the left side, I'm coming in to -3, and from the right side, I'm coming in to -3. And you can see that f of x, when x is equal to -3, f of x is also equal to, you can look on here, the y values at -3. So the limit as x approaches -3, and if I don't feel like writing out this full function, I can just refer to that as function f of x. My limit is also equal to -3. All right, let's look at number 4. The limit as x approaches -1. Now, as I'm approaching -1 from the left-hand side, you can see each time where I am on that linear piece. And I'm coming into -1. And you can see at -1, there's a jump in the graph. And I'm actually equal to this value down here. But if I'm looking from the left-hand side, the limit is -1. And if I'm looking from the right-hand side as I come into -1, f of x is equal to -3. But because this graph jumps here, and my limit is not the same from the left and the right-hand side, that means that the limit actually does not exist. So the limit as x approaches -1 of f of x is equal to does not exist. Ooh, that's an E. All right, if you were going to plug in -1 into both of these pieces, in order for it to be a limit, both of these pieces would have to be equal, and they are not. Example 5, find the limit as x approaches -1 from the left-hand side. Notice there's no graph for us, so we can actually graph it and find the limit, or we could use these two pieces. If I were going to plug into the two given pieces, I have to determine which piece is on the left-hand side of -1. So less than is going to be on the left-hand side of -1. So I would actually, if I was using direct substitution, I would plug it into that first piece. So let me go ahead and do that, as that is probably the easiest way to answer this problem. So I'm going to take -x subtract 3, and in place of x, I'm going to put -1. So it's -1 subtract 3, which equals to 1 subtract 3. And so the limit is actually -2. Graphically, this is what we would do. We would graph the first piece, so we would start at -3, and I just use dots to graph it. And the slope is down 1, right 1, or up 1, left 1. And this graph is only going to be the smaller to the left, the lower bound, because it says x is less than or equal to -1. So starting at -1, ooh, that's crooked, but this graph looks like this with this line here. Then we would erase those 2 points. Okay, so now that's the first piece, which is this piece. Now we're going to graph the second piece. So the second piece, I'll graph in purple. So now I'm going to graph that piece. So I would start at +1, and then the slope is 1 over 1. So up 1, right 1, up 1, right 1, up 1, right 1, down 1, left 1. Now, when I'm at -1, it says not included. So that's actually an open circle at -1. And I'm only looking for this part of my graph. So now looking at the limit, if I am coming into -1 from the left-hand side, I am going to be on this black function here, which is at -2. So that is a long explanation of question number 5. Looking at question number 6, has the limit as x approaches 2 of f of x. You could graph both of these pieces, or you could simply use direct substitution and substitute in -2 into both pieces. You would make sure that the answer is the same in order for there to have a limit that exists. So I'll do that. I think it's easier. So it's the opposite of -2 squared, subtract 4 times -2, subtract 5. When you simplify that all down, you're going to get -1. Second piece is there's nothing to substitute, so it actually equals -1. Check, check. Both graphs are the same, and so the limit as x approaches -2 of f of x is equal to -1. I want to show you what number 6 looks like if you were to solve it graphically instead of by direct substitution like we just did. So graphically what's going to happen is if f of x is equal to -1, that's a horizontal line. And that horizontal line is going to start at -2, but it's greater than -2, which means it'll be an open circle. So you've got this open circle and this horizontal line for that part of the piecewise function. The second part of the piecewise function is this quadratic equation. You could set up a table and plug in values quickly to figure out what that parabola looks like. If you put in -2 into this function here, you're going to get out a -1. if you put in negative 3, you're going to get out a negative 2. And if you put in negative 4, you're going to get out a negative 5. So starting at negative 2, negative 1, you can see that there's an open circle here, but this piece is a closed circle in the same place. So this is going to be a continuous function. So now if I go left 3 and down 2, and left 4 and down 5, this piece of the graph is a parabola. And because the function is continuous, when I find the limit as I'm approaching the left and the right-hand side of negative 2, from the left-hand side and from the right-hand side, this function is approaching the same point, which is negative 1. So therefore, the limit exists. Number 7, you can see I just quickly did by direct substitution. The important part of this problem was realizing which of these two sections or parts of the function I should directly substitute into. So since I was looking for the limit as x approaches 0 from the right, I picked the right-hand piece. This piece is greater than or equal to 0, which is on the right-hand side of 0. And number 8, before we begin it, I want to remind you what the absolute value of x looks like. The absolute value of x is really a piecewise function. So when x is less than or equal to 0, we always get the opposite of x, which is going to be this piece of the v. Then when x, the absolute value of x, if x is greater than or equal to 0, we get x, which is the positive piece of that piecewise function. Looking at this original problem, you will see if I take 0, which is what I'm approaching from the left-hand side, and I were to directly plug it in, I would get 0 over 0, which is an indeterminate. So that's not going to work. But I want you to see the behavior of this graph because it always ends up being the same. So if I were to take a table and I were to plug in, let's say we're going to start with negative 2. If I take the absolute value of negative 2 divided by negative 2. So this is the absolute value of x over x. When I put in the absolute value of negative 2, it's going to come out as 2. And I have a negative 2 on the bottom, and that's going to always equal negative 1. So at negative 2, this is going to be at negative 1. If I were to plug in negative 1, you're going to see that this is going to come out as negative 1 again. But when I plug in 0, it's undefined. So there's the first part of that function. Now, if I plug in a positive 1, when we take the absolute value of 1, we get 1, and 1 over 1 is 1. And if I plug in 2, the absolute value of 2 over 2 is also 1. And if I plug in 3, the absolute value of 3 over 3 is also equal to 1. And so this is what this function looks like. And anytime you have an absolute value like that, you're going to get this, it almost looks like a shelf. And it's a jump function. It's discontinuous, and the function jumps. And sorry, that's really crooked right there. Let me fix it. So now that we have the function graphed, we're going to take the limit as x approaches 0 from the left-hand side. So as I'm moving in towards 0 from the left-hand side, you can see that y, or the output, is always negative 1. So this limit is equal to negative 1. By the way, if I were finding the limit as x approaches 0 from the right-hand side, of this same function, f of x, it would equal positive 1. And if I were finding the limit as x approaches 0 from the left and the right, f of x would equal does not exist. On example 9, I'm going to use direct substitution. It says find the limit as x approaches 0 from the right. Since this is not a piecewise function, the left and the right side will be the same. So in place of x, I'm simply going to plug in 0, and the limit is going to equal 1. Number 10, find the limit as x approaches 1. Because there's no plus or minus, we have to find it from the left side and from the right side. So we're going to plug in 1 to the first function, so it'd be 1 over 2, x is 1, plus 9 over 2, which equals 5. Then we'll plug in 1 to the second function. 1 squared subtract 6 times 1 plus 10 is also 5. So what does the limit of f of x equals? It equals 5. In number 11, we have an absolute value problem that will have the same pattern as the problem that we did before, which was question number 8. So the first thing is, if I were going to do direct substitution, when I would plug in -1 here and -1 here, I'm going to end up with 0 over 0. So that is not going to work. So let's look at absolute value. So now I'm going to look at this absolute value function as a piecewise function. So if I break this up into the two pieces, I'm looking at the piece where in here is going to be 0. So I'll look at the first piece where x is less than -1, and the second piece where x is greater than or equal to -1. So if I take the absolute value of this and I have a number that's greater than or equal to -1, it's going to come out just as x plus 1. But if x is less than -1, then my value is going to come out as the opposite of x plus 1. So what I want you to notice is we have the absolute value of x plus 1 over the same thing, x plus 1. And what we notice is if the absolute value of x plus 1 are numbers that are less than -1, that part is going to come out as the opposite. And then because we have the same thing on the top as the bottom, we get -1 over 1. And we have this 3 over here, which means this is going to equal -3. So what this means is at -1, we are actually undefined. But everything smaller than -1 is equal to -3. All right, so if we look at the same thing again, but this time we take the absolute value of x plus 1 where the numbers are greater than or equal to -1, it'll come out just as x plus 1. So that means we're going to have a positive 1 over 1, which will equal +3. So at -1, we're undefined, but numbers that are moving in this direction will all give us 3. So looking at the limit, notice that the limit of -1 from the left side is -3, and the limit of -1 from the right side is +3. And so in number 11, the actual limit does not exist. Number 12, I'm out of room, but what we're going to do is use direct substitution. And we're going to substitute it into the first piece and into the second piece of the function. And if those numbers come out exactly the same, then we know that the limit as x approaches -2 exists. So to start it, we'll put in negative 2 squared, and that's equal to 4. Then we're going to put in the opposite of negative 2 over 2 plus 3. These two negatives will make a positive, which is 1 plus 3, which equals 4 as well. So since these are the same from the left and the right, we know that the limit as x approaches negative 2 is of f of x is equal to 4. So our answer to that one was 4. 11, does not exist. So on number 13, we want a two-sided limit, which means we could make a piecewise function. If I do the limit as x approaches, and you can pick any number, let's say 1, then f of x is equal to, and it wants a limit that does not exist, so you just have to make sure that your piecewise function jumps or breaks at the two places. So I could say f of x equals 0 and f of x equals 5, which are both just horizontal lines. And here I would have x is less than 1, and here x would be greater than or equal to 1. And this piecewise function does not have a limit. On number 14, it says, give an example of a two-sided limit function with an absolute value where the limit does not exist. So this one you could do anything with absolute value. It's going to give us that shelf-looking graph where we get a discontinuous function that jumps. The limit as x approaches 0. You could use one that we've already done, the absolute value of x over x, which does not exist. Another one would be the limit as x approaches 1 of the absolute value of x minus 1 over x minus 1 does not exist. Thanks, you guys. Have a good day.